scanner, so that big tube that many people probably are familiar with, to look inside the living human brain and look at the structure of those connections. So not so much the function that you would get when you measure the speed of connection, but really the anatomy of those connections, where they are, what they connect to.
Are you putting living, breathing people in this MRI, or what else might you be doing?
Yes, we do most of the time, not all the time. But ideally, we would image living, breathing people in the MRI scanner, and it's completely non-invasive. So you can go in there, you can even have a nap whilst we take those pictures. So it's, for some people, it's quite a pleasant environment.
Wow, I cannot imagine that. I've had a brain scan and an MRI. It is not a pleasant situation. I have claustrophobia, so that would do it, right?
Yeah, that doesn't help.
But you also look at post-mortem brains too, right?
Correct. So we look at post-mortem brains sometimes in the MR scanner, but we also actually look at them in the morgue and do actual Klingler post-mortem dissections, and that lets you really carve out the white matter connections between those brain areas in the actual brain. So when we use the diffusion-weighted imaging tractography, it's a proxy of the anatomy because it's based on how water molecules move around in the brain. And if you have areas where there's no restrictions, so for example, there's these holes basically in the brain that are filled with liquid to cushion the brain when we walk or hit our head, then the water molecules can freely move around in all different directions and there's no restriction. The water molecules within those white matter connections, however, they're limited by the surface of those connections. So it's basically like a straw, and they travel faster along the direction of the axon, so that connection, and they're hindered in the perpendicular direction. And this is what we actually pick up with the MRI machine. So it's an indirect estimate of where those connections are, whereas Klinger postmortem dissection actually lets you see them in real life.
How did you discover, or how did people discover that this technique you're using would be a good way of studying the connections in the brain?
So there's this famous saying that someone's noise is someone else's signal. And what that means is that when you acquire images in an MRI machine, there is a lot of noise in the data. And for many years, we thought we need to get rid of this noise. It's disturbing the signal that we're interested in, which is the anatomy. And then people started realizing that actually within this noise that is in the images, there is some patterns, there's some information that we could actually use and study. And this is how diffusion tractography was invented, or resting state imaging these days, for example.
Yeah, that reminds me in physics and astronomy of accidentally discovering the cosmic background radiation because they thought there was noise in the receiver. So this is an interesting parallel.
Yeah, exactly.
The idea of defining the functions of brain regions, let's talk about how old that is, right? Where did it come from?
So defining the function of brain regions is actually a very old way of doing clinical anatomical correlation studies, and that really comes from seeing patients in the beginning. So we have a series of famous cases to actually establish the neurosciences as we know them today, and that is because those famous cases had a damage to their brain. So quite famous, for example, is Phineas Gage, who had an iron rod that flew through his skull and his brain and then landed a couple of meters behind him, and that iron rod damaged a part of his brain in the frontal lobe. He could still talk, but what had changed was his personality, his inhibition. So that is one of the famous cases that plays personality and its so-called executive functions in the frontal lobe. Another famous case is patient Tom, and he's known as patient Tom because he suffered a stroke to the frontal lobe, again a different part, and he could only utter the word temps. It was French, hence the slight imitation of an accent here. And that placed the articulation of language in the posterior frontal lobe. What these patients allowed people to do is to look at the brain and look at what function the patient lost. And that was then put together as in, if you lose the function after damage to this part of the brain, then this part of the brain is responsible for this kind of function. And this is where this area to function mapping originated.
quite interesting. Can you also, using this model, help us better understand how the human brain evolved?
Yes, absolutely. So, as we said before, ideally we put living, breathing humans in here. So you can also put non-human primates in this scanner, for example, macaques or sometimes even chimps. And that lets us study the white matter in different species. And then by proxy, you can make deductions about when the white matter changed between the species, and that would give you an indication of when certain cognitive functions may have evolved in the human brain.
Such as language?
Such as language, for example, yes.
So some monkeys may have some, but not all the connections in the brain, so to speak, that we have.
Correct. So there's a very prominent language connection that we call the arcuate fasciculus, which means the arching fiber bundle. And you can see a precursor of that in the monkey brain, but it's not the full connection. So it doesn't reach exactly the same cortical areas, and it's not as prominent as it is in the human brain, for example.
You know, of course, everyone's brain is a little bit different, right? How can this networking idea help you understand the individual differences between the brains, all of our brains?
So what we have done for decades of neuroimaging is that we wanted to know how the brain works, what's the function and the structure of the typical brain. And in order to do that, you take a picture of a lot of individual brains and then you bring them all together in a reference space where they all look the same, so you then compare them across the group. Now what we can do nowadays is, because we have a lot more data available and we have new analysis tools available, we can actually look a lot more into detail into each and every single individual brain. And what we have done back in 2008, for example, is look at the variability of the white matter. And what we could see is that there is a gradient in the brain, whereby older parts of the brain tend to be less variable, meaning they're more alike between us, and newer parts of the brain and the areas that are related to cognitive functions using functional imaging studies or lesion studies were actually highlighted as being more variable. So there's this beautiful gradient of variability in the brain.
Yeah, so would it be possible then to map how, say, a mental health issue or someone's personality changes the structure of the brain?
To a certain extent, yes. So there's already group studies that would compare people with certain neurological or psychiatric disorders to so-called healthy controls and see what is different in those brains. What you can also do is look at clinical populations. Again, this could be neurological or psychiatric patients, and follow them over time, so in a longitudinal study design, and see how the brain, that could be the gray matter or the white matter, changes throughout time.
This is Science Friday from WNYC Studios. In case you're just joining us, I'm talking with my guest, Dr. Stephanie Forkel, about the importance of understanding how brain regions are connected. Now, of course, we have those two hemispheres of the brain, as you mentioned. What can looking at these connections help us better understand about the functioning, possibly the different functions of the left and right brain?
So there's this conception that we have a left brain and a right brain, and the functions are dramatically different. So classically speaking, the left hemisphere is important for language and spatial attention, for example. Now, one thing that we need to consider is that those two hemispheres are densely connected by white matter. So they're not freely floating around in our skull, but they're actually densely connected. And every part of the left hemisphere is connected to every part in the right hemisphere, pretty much. And that means that some of the functions can be traced in both hemispheres. Now, obviously, the way we look at function these days, for example, is at language. We often look at the production and the comprehension of language. But language is a lot more, right? There's intonation, there's prosody, there's understanding humor, for example, or when we think about idioms, you understand the meta meaning of the words. And some of those functions are actually performed by the right hemisphere and not the left hemisphere. So what we sometimes see, for example, is that patients who suffer a lesion to the right hemisphere, they can articulate themselves, they can understand language, but when they talk, it's very monotonous. So there's this clear-cut division of this is what the left does and this is what the right does is not really appropriate. And also when it comes to recovering from brain damage, we can see that there's also some dynamic interaction between the left and the right trying to recover some of the function.
So how can your network model help scientists come up with better treatments for people with brain injuries or neurodegenerative disorders?
So what we have seen in clinical studies is that when you only look at the gray matter lesion, so where the lesion is located on the surface of the brain, we can explain some of the variance that we see in the recovery of people, but not all of it. Whereas if we look at the networks that are actually disconnected by a lesion, that explanationary power increases dramatically, and we still can't explain all of the recovery that we see, but at least a larger part than just looking at the lesion location itself.
Let's talk about what the next big question. I'm always interested in where you're heading with your research. What's the next big question you're looking to understand about the brain?
So in my own research, I'm currently trying to understand the magnitude of variability. So it's well established that our brains are different, and we have beautiful maps showing the variability of certain parts of the brain. And we, as I mentioned, did this study in 2018 where we looked at the variability at the group level. But I'm really trying to bring this to the individual brain now and map the magnitude of variability and what that magnitude then means for our cognition in health and in disease.
Do you think it's possible the brain has got, how many billions and billions of cells in it? Is it possible to understand our brain, do you think, completely and even get to consciousness someday?
The Holy Grail.
I had to ask that question.
I think I'd be surprised if we managed to get there in my career, but it's worth trying.
Good answer. Thank you for taking time to be with us today.
My pleasure. Thank you.
Dr. Stephanie Forkel, Assistant Professor at the Donder Center for Cognitive Neuroimaging at Radboud University, based in Nijmegen in the Netherlands. And that does it for this week. If you missed any part of the program or you would like to hear it again, sure, subscribe to our podcasts or ask your smart speaker to play Science Friday. And of course, you can say hi to us on social media, Facebook, Twitter, Instagram, or email us. Yes, the old-fashioned way, scifri@sciencefriday.com. Please send us feedback. Tell us what you'd like us to cover. Have a great weekend. We'll see you next week. I'm Ira Plato.